So I think roughly the first hour, we're just going to go through ordinary like characteristic zero linguistic theory, and then sort of show that we can kind of make sense of this in the modular settings, and then go through some array stuff. So the setup is as follows: is G is going to be a connected reductive group over K, which I think here we can just happily think of as the algebraic closure of FQ. The most important connected reductive, the most important thing here is that the group actually is defined over FQ itself, right? So that means that we have this Frobenius endomorphism, which goes from G to G. And typically, you can just think of it as taking a matrix and just raising all the entries for power Q. This is not at all general, but for the groups that we're mostly interested in, I think it's good enough. So now I'm going to define.
So what are the examples we should have in mind?
You should think of G, GLN, SON, some selector groups if you like. Do any other groups exist other than these, really?
I don't think so.
Maybe just to be picky, so you said G is defined over FQ bar, and then you said then we have, which is not really true though. So it's, you have G connected over FQ,
yep,
and then you consider the extension of scalars to FQ bar, and on that you have Frobenius.
Yeah, so I suppose more formally, I have some group called G naught, and really what I mean is that this is extension of scalars, right? Yeah. And then attached to this like FQ structure, I get a Frobenius endomorphism on the group over collection. Okay.
So in the case of like GLN, this you need this as just to say that the determinant is non-zero. All of it that just uses integer coefficients. So you can think of that as just FP coefficients to define that. So it's defined over the field FP. It's all its equations that define it, are defined over FP.
Yeah. All good. Okay, so then I'm going to define this variety X, which I'm just going to say is all the Borel subgroups inside of G. Right? And this has an action of G on it by conjugation, which makes sense because all the Borel subgroups are going to be conjugate. Okay.
So what's the definition of Borel subgroup?
Alpha triangle matrices. All good?
Oh.
What?
Anything you get by conjugating them in the GLN case, is that what you mentioned?
In general. Over algebraic closure, all the Borel subgroups, whatever they are, they're all conjugate by some element of G.
So in some cases it looks like that.
In some cases, yes.
In some cases, yeah.
In some cases.
Yeah. All good? Okay, so then now if we pick an F-stable Borel subgroup, so what this means is that, probably what you think it means, that the Borel subgroup is stable under the action of F. So let's say FB is equal to B. Then we can make the identification that the group modulo the Borel subgroup is isomorphic to X. And the isomorphism is simply provided by taking something here, just mapping it to conjugate. Right?
So it's probably useful for those who haven't seen this, is that the Borel subgroup is self-normalizing. So this is really a bijection. You don't lose information by considering a Frobenius class. Like, it's
Yes.
complicated.
Why is it important that B is stable?
Why is it important?
You want F to act on the right-hand side,
Yeah.
like F, a priori F doesn't act on the variety orbital.
So you choose it. Yeah, I guess if you take the. Yeah, I don't see why that would be true.
But yeah, F should act on the variety. Maybe
Maybe it doesn't, I don't know.
It's what gives you a base point that's fixed by F.
It's not the next one. So maybe it doesn't have to grow. I don't know.
Maybe like for that map to be Frobenius equivariant, so for that map to be defined over F cubed, one needs this to be an F-stable model. You know, like think about, well, he'll do this in a second, but think about P1. So F-stable lines are points of P1 over F cubed, and all the rest are not F-stable lines.
Okay, great. So we have this variety with action of G on it by conjugation. And so now I want to look at the orbits of this action. And the claim is that, well, I actually want to look at the G orbits on the product of this. Okay? And the claim is that I can identify these G orbits with the Val group. So Gx here. It won't be good. Okay. This comes from the Breuer decomposition. And this is going to be G1B and G1B. Thanks to this isomorphism here. And this is also isomorphic to now. Yes, by definition. Well, by this isomorphism. Okay. So then we say that, so this is definition, that two Borel subgroups are said to be, oh, I'm going over, said to be in relative position W. If they belong to the same orbit. So if this and this belong to here, where this denotes the orbit associated to W under this identification. And so now we can actually define the Delian-listic variety. So now this is the all-important Delian-listic variety. So this is going to be the subvariety of X, such that is the subvariety, which I'll denote by this, and this contains all the Borels. So the Borels, such that B and the Frobenius of B are in relative position W. So there's a few ways that one can think about this, is that this is kind of like the orbits acting on, the set of orbits in this space here, intersected with the graph of the Frobenius. So you can call it this, where this will just be. Right? Okay. So this is like one of the main players of the talk, if you will. What we're going to see is that we have like an action of the finite group associated to G, the set of fixed points, together with the maximal torus. And this is really important because now we're in the situation where we have an action like on some sort of space, then we can do this like sort of linearization process to then get like an action on a bunch of vector spaces. So in other words, representations, right? So there's actually like a much neater way of putting this. So if you wanted to, you could really forget about everything that I've just said. So I can just define this as follows. So here B is going to be F-stable. F-stable. Then this variety is going to be equal to something inside of this flag variety. Where okay. So observe that this has a, I think, right action, no, left action of G. So the finite group set of FQ points of the group. But we don't have an action of like a maximum torus or anything like that yet. So you can observe that we have this action here because like the action of the group doesn't change like the relative position of the Borel subgroups. So if I act on the left here, then it's going to like pull out and it's all going to be equal, right? And so, okay, this is good. And we also now have another variety, which I wish I wrote this differently, that sits above this one here. And this is going to be completely analogous thing. Where U is the unidependent radical of the Borel. Okay. And so this actually does sit above this variety here. So we have a map from Y into X. And this again is equipped with an action of a finite group. And then an action of the maximal, or the F fixed points of the maximal torus associated with W, which I think we have certainly seen in this course before.
So this is like a non-split torus.
Yeah, it could be non-split. So basically when W is like non-trivial, then you've got to be looking at the other FP rational tori. Right? And so you can check that this actually does have an action of the torus. I think it's probably a good exercise to do that, but I don't think we're going to do it here. And so this map that I said that I claim that we have, it's simply just induced by the map from this to this, which sends GU to GB. Okay. And the claim is that this map itself is actually simply just quotienting by this maximal torus here. Okay. Which will become quite a useful fact later, I think.
The ISO GLN, so the J-mod based flag variety. Well, it's J-mod U. It's just that's good. That's closer, but sorry. Yes.
Isn't it like the flag variety when you have an extra, you have like a torus worth stuff of each point in your flag variety? Like it's, yeah, the total space of like a torus bundle over the flag variety.
Yeah, something like this.
And I guess the point over like a Borel is the Borel mod the uniphoton radical flag. So that like canonically gives you torus looking thing living over each Borel in the total space of action you do.
Yeah, I somehow say that there's like a torus worth more stuff in that space because like when the quotient type B, when it contains like a torus.
Shouldn't it like
The
the
torus
torus
is
exactly
built.
be you take something like either the tangent or cotangent bundle on G mod B and the zero section?
No.
No? Oh,
It's described, if you want to know what it is, it's described in Bernstein. And you can describe it as like, it's very similar to what Chris is saying, like Borel subalgebra plus some isomorphism, plus some T equivalent isomorphism of B, or the commutative with blah. But what maybe a nice thing to remember is for SL2, what is it? C2 without zero, yeah? because the stabilizer of like the vector 1, 0 is exactly the unipotent radical. And you can move that vector anywhere except the 0.
Right, so SL2 acts on C2 minus 0
By acting on 1, 0.
on the stabilizer is
You. You the group, not you.
okay. Yeah, that makes sense. All right.
And you see like C2 without the origin has a beautiful map down to P1. You probably encountered before that is indeed a T bundle.
Yeah.
Non-trivial T bundle. Called the tautological bundle. And another mathematical horror show is the fact that we call G mod U base affine space, even though it's never affine.
What you call G mod U affine space.
It's called base affine space.
Base affine space. With base means it's got nothing to do with.
An affine. It's got nothing to do. It's not affine.
Oh,
All good?
Yeah.
Yeah, so first example is if we just look at W trivial, then this variety is simply going to be equal to the FQ points of this quotient. So right. And now let's look at a more interesting example. So now if W is like the non-trivial element, so you can also write this as a matrix. And that's actually, let's say, G is equal to SL2 now. Well, thanks to, again, the Bruja decomposition, we have that the group G is going to be the Borel subgroup together with this other group here, right? And so this kind of tells you that, well, this thing is going to be like G, but without like all the stuff in the Borel. So this says that BSP is going to be equal to this bunch of things here, with C some non-zero thing in your field. Right. And this is also true of this thing here. But now I have a 1 in the column. Okay. So now I want to try and make some hopefully useful identifications. So I can identify A2 without 0 with G mod U. And the map is simply there, right? This is a good exercise to do it once again. And now I can also identify P1 with the flag variety, as one has probably seen many times, by just going X, Y, V. Okay. So just recall that this is going to be equal to all the things here. So I basically just want to like write this down and then see exactly when it's in here and when it's in here, right? So this immediately tells us that I'm not going to do the full computation, because that was kind of the point of making this identification here. This is going to be equal to, and then the Frobenius raises everything to the power of Q. And so you go multiply this out now, and then you'll just have a bunch of stuff up here, bunch of stuff up here, stuff up here. And then in this diagonal corner, you have this. Okay? So now we can write down what the y is. Well, because of our computation here before, we have that this thing is just equal to 1. So it's going to be all the set of all the stuff in A2 without 0, such that equal to 1. And this sits above this variety now. And it's given by the same thing, but now in projective space. Where this is not equal to 0. Okay? And this is really, really nice. This is very famously known as the Drinfeld curve. I suppose after the person that was probably first interested in it. So Drinfeld realized at some ridiculous age, like 19 or 20, right, that a lot of the representations of SL2 FQ actually appear in the cohomology of this curve. How he did that, I have actually no idea, because he must have been 19 at the time, and the tau cohomology was probably like 15 years old by that point. So I don't know how he saw this, but he did, and it somehow was one of the main inspirations behind the linguistic theory. And then another final remark is that this space is going to be isomorphic to P1, but without the FQ points of P1. You can kind of convince yourself with this, because if I had a point which was defined over FQ, then, well, say for example, X would be equal to X to the Q, and then this equation here would actually then equal 0, which
You just maybe moved your Q's under, you can do the same thing, X y to the Q minus y to QX.
Oh, yeah, I'm an idiot.
Split over X.
X. Pretty cool, right?
So one cool thing from this as well is that you take P1, which ought to be like a 2-sphere, you remove Q minus 1 points from it, and suddenly it has this incredibly interesting covering space. And and that's where your geometry intuition has to sort of go out the window. What was that? Q plus 1 points, yeah, sorry. So you take what should be an S2, you remove Q plus 1 points from it, and it suddenly has a really big covering space. Much, much, much bigger than anything that could happen with an actual sphere. Right, because it's got Frobenius stuff.
Over K, which I think here we can just happily think of as the algebraic closure of FQ. The most important connective reductive. The most important thing here is that the group actually is defined over FQ itself. Right? So that means that we have this Frobenius endomorphism, which goes from G to G. And typically, you can just think of it as taking a matrix and just raising all the entries to the power of Q. This is not at all general, but for the groups that we're mostly interested, I think it's good. So now I'm going to define.
So what are the examples we should have in mind?
You should think of G, GLN, SLN, symplectic groups if you like. Do any other groups exist other than these, really?
I don't think so.
Maybe just to be picky, so you said G is defined over FQ bar, and then you said then we have, which is not really true though. So you have G connected over FQ,
yep.
And then you consider the extension of scalars to FQ bar, and on that you have Frobenius.
Yeah, so I suppose more formally, I have some group, call it G naught. And really what I mean is that this is extension of scalars. Right? Yeah. And then attached to this like FQ structure, I get a Frobenius endomorphism on the group overflation. Okay.
So in the case of like GLN, this you need this as just to say that the determinant is non-zero. All of it that just uses integer coefficients. So you can think of that as just FP coefficients to define that. So it's defined over the field FP. It's all its equations that define it, are defined over FP.
Yeah. All good. Okay, so then I'm going to define this variety X, which I'm just going to say is all the Borel subgroups inside of G. Right? And this has an action of G on it by conjugation, which makes sense because all the Borel subgroups are going to be conjugate. Okay.
So what's the definition of Borel subgroup?
Alpha triangle matrices. All good.
Oh.
What?
Anything you get by conjugating them in the GLN case, is that what you mean?
In general. Over algebraic closure, all the Borel subgroups, whatever they are, they're all conjugate by some element of G.
So in some bases, it looks like that.
In some cases, yes.
In some cases, yeah.
In some bases.
All good. Okay, so then now if we pick an F-stable Borel subgroup, so what this means is that, probably what you think it means, that the Borel subgroup is stable under the action of F. So let's say FB is equal to B. Then we can make the identification that the group modulo the Borel subgroup is isomorphic to X. And the isomorphism is simply provided by taking something here, just mapping it to conjugate. Right?
So it's probably useful for those who haven't seen this is that the Borel subgroup is self-normalizing. So this is really a bijection. You don't lose information by considering a conjugacy class. Like
Yes.
it's a conjugate.
Why is it important that he is F-stable?
Why is it important?
You want F to act on the right-hand side,
Yeah.
like F, a priori F doesn't act on the variety of Borel. So,
So you choose it. Yeah, I guess if you take yeah, I don't see why that would be true.
but yeah, F should act on the variety. Maybe
Maybe it doesn't, I don't know.
It sort of gives you a base point that's fixed by F.
That is not the next work. So maybe it doesn't have to grow high. Oh, I don't know.
Maybe like for that map to be Frobenius equivariant, so for that map to be defined over FQ, one needs this to be an F-stable Borel. You know, like think about, well, he'll do this in a second, but think about P1. So F-stable lines are points of P1 over FQ, and all the rest are not F-stable lines.
Okay, great. So we have this variety with an action of G on it by conjugation. And so now I want to look at the orbits of this action. And the claim is that, well, I actually want to look at the G orbits on the product of this. Right? And the claim is that I can identify these G orbits with the Val group. So GX here. It won't be what. Right. This comes from Bruja decomposition. And this is going to be G1B and G1B. Thanks to this isomorphism here. And this is also isomorphic to now. Yes, by definition. We'll find this isomorphism. Right. So then we say that, so this is definition, that two Borel subgroups are said to be, oh, I'm going over, said to be in relative position W. If they belong to the same orbit. So if this and this belong to here, where this denotes the orbit associated to W under this identification. And so now we can actually define the delinguistic variety. So now this is the all-important delinguistic variety. So this is going to be the subvariety of X, such that is the subvariety, which I'll denote by this, and this contains all the Borels. So the Borels, such that B and the Frobenius of B are in relative position W. So there's a few ways that one can think about this. Is that this is kind of like the orbits acting on, the set of orbits in this space here, intersected with the graph of the Frobenius. So you could call it this, where this will just be. Right? Okay. So this is like one of the main players of the talk, if you will. What we're going to see is that we have like an action of the finite group associated to G, the set of fixed points, together with the maximal torus. And this is really important because now we're in the situation where we have an action like on some sort of space, then we can do this like sort of linearization process to then get like an action on a bunch of vector spaces. So in other words, representations, right? So there's actually like a much neater way of putting this. So if you wanted to, you could really forget about everything that I've just said. So I can just define this as follows. So here B is going to be a stable. Then this variety is going to be equal to something inside of this flag variety. There. Okay. So observe that this has a, I think, right action, no, left action of G. So the finite group set of FQ points of the group. But we don't have an action of like a maximal torus or anything like that yet. So you can observe that we have this action here because like the action of the group doesn't change like the relative position of the Borel subgroups. So if I act on the left here, then it's gonna like pull out and it's all gonna be equal, right? And so, okay, this is good. And we also now have another variety, which I wish I wrote this differently, that sits above this one here. And this is going to be completely analogous thing. Where U is the uniform radical of the Borel. Okay. And so this actually does sit above this variety here. So we have a map from Y into X. And this again is equipped with an action of finite group. And then an action of the maximal, or the F fixed points of the maximal torus associated with W, which I think we have certainly seen in this course before.
So this is like a non-split torus.
Yeah, it could be non-split. So basically when W is like non-trivial, then you've got to be looking at the other FP rational tori. Right? And so you can check that this actually does have an action of the torus. I think it's probably a good exercise to do that, but I don't think we're going to do it here. And so this map that I said that I claim that we have, it's simply just induced by the map from this to this, which sounds GU to GB. Okay, and the claim is that this map itself is actually simply just quotienting by this maximal torus here. Okay, which will become quite a useful fact later, I think.
The ISO GLN, so the J mod based flag variety. Well, it's J mod U. It's just that's good. That's course sorry.
Yes.
Isn't it like the flag variety when you have an extra, you have like a torus worth of stuff of each point in your flag variety? Like it's, yeah, the total space of like a torus bundle over the flag variety.
Yeah, something like this.
And I guess the point over like a Borel is the Borel mod the unipotent radical factor. So that like canonically gives you torus looking thing living over each Borel. The total space of that should be unique.
Yeah, and somehow say that there's like a torus worth more stuff in that space, because like when the quotient type B, when it contains like a torus.
Shouldn't it like
The
the
torus
torus
is
exactly
built.
be you take something like either the tangent or cotangent bundle on G mod B and the zero section?
No.
No? Oh,
It's described, if you want to know what it is, it's described in Valence and Bernstein. And you can describe it as like, it's very similar to what Chris is saying, like Borel subalgebra plus some isomorphism, plus some T equivalent isomorphism of B, or the commutative with blah. But what maybe a nice thing to remember is for SL2, what is it? C2 without zero, yeah? Because the stabilizer of like the vector 1, 0 is exactly the unipotent radical. And you can move that vector anywhere except the 0.
Right, sorry. So SL2 acts on C2 minus 0
By acting on 1, 0.
on the stabilizer is
You the group, not you.
okay. Yeah, that makes sense.
And you see like C2 without the origin has a beautiful map down to P1. You've probably encountered before that is indeed a T bundle.
Yeah.
Non-trivial T bundle, or the tautological bundle. And another mathematical horror show is the fact that we call G mod U base affine space, even though it's never affine.
What you call G mod U affine space.
It's called base affine space.
Base affine space. With base means it's got nothing to do with.
An affine means it's got nothing to do. It's not affine.
Oh,
All good?
Yeah.
Yeah, so first example is if we just look at W trivial, then this variety is simply going to be equal to the FQ points of this quotient. So right. And now let's look at a more interesting example. So now if W is like the non-trivial element, So you can also write this as a matrix. And that's actually, let's say, G is equal to SL2 now. Well, thanks to, again, the Breuer decomposition, we have that the group G is going to be the Borel subgroup together with this other group here, right? And so this kind of tells you that, well, this thing is going to be like G, but without like all the stuff in the Borel. So this says that BSB is going to be equal to this bunch of things here, with C some non-zero thing in your field. Right. And this is also true of this thing here. But now I have a 1 in the column. Okay. So now I want to try and make some hopefully useful identifications. So I can identify A2 without 0 with G mod U. And the map is simply here, right? This is a good exercise to do it once again. And now I can also identify P1 with the flag variety, as one has probably seen many times, by just going X, Y, B. Okay. So just recall that this is going to be equal to all the things here. So I basically just want to like write this down and then see exactly when it's in here and when it's in here, right? So this immediately tells us that I'm not going to do the full computation because that was kind of the point of making this identification here. This is going to be equal to, and then the Frobenius raises everything to the power of Q. And so you go multiply this out now, and then you'll just have a bunch of stuff up here, bunch of stuff up here, stuff up here. And then in this diagonal corner, you have this. Okay. So now we can write down what the Y is. Well, because of our computation here before, we have that this thing is just equal to 1. So it's going to be all the set of all the stuff in A2 without 0, such that equal to 1. And this sits above this variety now. And it's given by the same thing, but now in projective space. But this is not equal to 0. Okay. And this is really, really nice. This is very famously known as the Drinfeld curve. I suppose after the person that was probably first interested in it. So Drinfeld realized at like at some ridiculous age, like 19 or 20, right, that a lot of the representations of SL2 FQ actually appear in the cohomology of this curve. How he did that, I have actually no idea, because he must have been 19 at the time, and the tau cohomology was probably like 15 years old by that point. So I don't know how he saw this, but he did, and it somehow like was one of the main inspirations behind the linguistic theory. And then another final remark is that this space is going to be isomorphic to P1, but without the FQ points of P1. You can kind of convince yourself with this, because if I had a point which was defined over FQ, then well, say for example, X would be equal to X to the Q, and then this equation here would actually then equal 0, which
You just maybe moved your Q's under, you do the same thing, X y to the Q minus y to QX.
Oh, yeah, I'm an idiot.
Put it with X.
X. Pretty cool, right?
So one cool thing from this as well is that like you take P1, which ought to be like a 2-sphere, you remove Q minus 1 points from it, and suddenly it has this incredibly interesting covering space. And this and that's where your geometry intuition has to sort of go out the window. What was that?
Q plus 1.
Q plus 1 points, yeah, sorry. So you take it, what should be an S2, you remove Q plus 1 points from it, and it suddenly has a really big covering space. Much, much, much bigger than anything that could happen like with an actual sphere. Because it's got Frobenius stuff.
So what XW and YW, what are they? The varieties over FQ bar?
Yes.
Yep.
Okay. So P1 minus those points means the FQ bar points.
Yes.
That don't live in.
That don't support.
So that's an
We're
example.
identifying things. We're thinking of these as the FQ bar points here.
I would say that you're thinking, so imagine that I have a variety over FQ. That's a finite. Then it has finitely many FQ points. And so, like, I imagine I have this big thing, and then I have, like
Bunch of dots around.
a bunch of dots, finitely many dots. And now I can do a pointless thing, which is to remove all of these points, and then I create a variety that is pointless. It has no FQ points whatsoever. Yeah. Maybe Nick, would you like to draw a picture of Chris's P1 without, just so it's in everyone's mind?
What was his picture again?
So he's just saying take P1 and just remove Q plus 1 points from it.
Circle?
Well,
Or
for
a
me
sphere.
it's a sphere. P1's a sphere. Yeah. And then somehow we're thinking about this as an object, positive characteristic algebraic geometry.
But is it really a sphere?
I mean, yeah,
So P1 FQ bar
P1 of FQ bar is really a sphere.
is topological.
It's not really topologically a sphere, but it really is a sphere. I have to believe
Yeah, I
that.
just don't know.
Like,
Well,
if,
it's
if
like,
FQ
do you believe-
bar was C,
I mean,
it
it's
would be.
like, is this a circle?
Yeah, well,
It's a sphere and
I'm just imagining it as a sphere.
Yeah, okay.
And now it has Q plus 1 points in it, which are little dots.
Yeah.
And we just take them away.
Yeah.
Okay. So in this particular case, we have P is 4.
Q is
Q is 4, which is allowed. Now, what Chris is saying, so if you look at that object as an object of complex algebraic geometry, so if you take P1 and you remove 5 points from it, its automorphism group is very small. But somehow in this characteristic P world, we have this big, rich automorphism group of S1 2 AQ. Maybe now that we're just, yeah, sorry Nick to keep interrupting, but that's life.
No,
You've got to get used to it.
more fun.
So can you write SL2 FQ acts on this?
Or you want SL2 or SL2?
That's perfect. Yeah, so that acts on this picture. Now, question to the audience. Does SL2 act on this? Does SL2 of the FQ bar points act on this? So it moves, any point can be moved to any other point. So it definitely doesn't preserve this magic little subset of rational points. Now, that is very important for the following reason. So we have an action of a finite group that does not extend to an action of FL2 FQ bar. This is important for the following reason. Imagine that I have a connected group acting on a space, and I take cohomology. you mind if I run on the board? Sure. It's just very, I think it's like incredibly important, so we can bang on about it for as long as we want. G is a connected group acting on X. Now, question for everybody bar CH. How does G act on the cohomology of X? But Jordy, you haven't told me what X is, and you haven't told me what G is. How can I possibly know the answer? What do you reckon, Isaac? A very hard question, so you're allowed to say no idea.
And I like to do an analogy with K theory.
Sure.
So you take an element of K theory, that's the vector bundle over X,
Mm-hmm.
and then you could pull it.
Pull it back. That's phenomenal. Yes. Pull it back. Get a new vector bundle. What do you know about this new vector bundle?
So you're pulling it back on a group element,
Along a group element. Yeah.
which is like convertible.
Yeah.
So it shouldn't like mess up the vector bundle too badly.
Yeah. You're within epsilon of the answer. Okay. So let me give you a bit more clue.
Okay.
So here's G, and this is what G looks like. Yeah. It's connected. So it's a big thing like this. And in here I have the identity, and then I have my element G.
Oh,
So these,
so there's a part.
there's a path.
Right.
So that means that the pullback along G and pullback along the identity are homotopic. So the action of any element of G is homotopic to the identity. So do you want to finish the punchline up here?
And pull back along homotopy equivalent map size model.
Mm-hmm.
And so it should be isomorphic to itself. Like to the original pull.
Exactly. Correct.
So it does nothing.
Does nothing.
Right.
Exactly. It's trivial. Yeah. So connected group actions on cohomology are trivial. Yeah. So if this extended to SL2F bar, and we believe that everything is like over the complexes, which is actually is, then we have trivial action. But the fact that this does not extend is critical to everything. But I guess the thing here is that these spaces are incredibly rich.
Yeah.
Yeah.
And if you try and like you just tried to do this, like you took a finite group sitting inside GLN, I don't know, removed a bunch of points, you looked how it acted on the complement or something. Doing that in a more complicated way very rapidly gets to complicated spaces, which are like very, very complicated and not in a good way. Like here, you know, it's a complicated, it's a very rich space, but it's not like unavoidable complication. Whereas if you try and do this for like an unstructured object, you get a bunch of stuff
And it's complicated.
and it's complicated.
Okay, so we have a bunch of varieties and they have an action of a finite group, as we just discussed, and they have an action of a maximal torus. So I'm sure this is probably not controversial to say, is that because we have this action on this group now, then this induces a linear action on its cohomology. So then we have the cohomology groups, and then bimodules, okay? So these are the analytic cohomology groups. I'm just going to write it for Y. So these are the coefficients in QL bar. The cohomology groups. So these are GF, GWF, bimodules. Okay. I think Chris gave a very good explanation probably a few weeks ago. It was like, this is, you could think of C, but nicer, I guess. Right? But in any case, like, don't be scared by it or anything. It's just think of it as like these nice groups attached to a space and then have a happy life.
And so this, like, in the analogy with why should P1 be thought of as a sphere, or why should it be thought of as S2? It's going to have a non-zero cohomology group in degree 0 and in degree 2. And that's it. And that's what a sphere looks like. So in that sense, these things look like topological attachment.
Okay, great. So we now have a group, a finite group acting on this, and then a torus acting on this from the other side. So now we can define a bunch of representations. Okay, so definition. the Delinean listing representation. So this is going to be associated to a W, because we're going to be looking at the cohomology of the W Delinean listing variety, and a character of this finite maximal torus. This is going to be a definition. We'll denote it like this. And this is the sum, the alternating sum of the cohomology groups. Where here I take the theta isotypic component of this, right? So you can think of this as like if V is in the cohomology, then we're asking for all the vectors that act by the character theta, right? So this is actually like a representation, or strictly a representation because it lives in Earth and D group. So this is a virtual representation of the finite group G, because essentially what we've done here is like by taking this isotypic component in the cohomology, you're kind of like fixing the action of T, and then you then get an action of G, right?
All right, I'm confused. TWF, that is an algebraic group, an algebraic torus?
No, it is a,
Oh, it's fixed points?
yes, it's the like FQ points of one of the maximal tori in a group. So for instance, if G were SL2, as we saw before, you have like, we have these two sort of maximal tori. One that's kind of lives over the quadratic extension, and one that's split over the base, right? So we have like T, which looks like this, right? And then T, which is twisted by this element in W, which is going to look like, someone correct me.
These are both like FQ points of some like non-split torus defined over some smaller subfield.
Yeah, so D is going to be a non-square in your finite field, right? So how you get this torus is essentially by like thinking of this as living in the automorphisms of the quadratic extension of FQ. Okay. Which you can identify with GL2.
Maybe another, like I think this is probably obvious, but like, you know, if I have some variety over C, I can ask in how many ways is it defined over R? So like a conic is, you know, defined in 3 ways over R or something. And then I can say, in how many ways is my torus defined over FQ? And it turns out that this is parameterized by conjugacy classes in the file for a split group. So and each of these, so TWF is the FQ points of the torus potentially non-split given by the conjugacy class.
This is like potentially like, this is actually a non-obvious point that I'm kind of haven't spoken about, is that the tori living in your group are parameterized by like conjugacy classes in your file group. Hence this notation.
And in the case of GLN, you can make this really explicit because like the torus morally should just be products of K star, where K is your field of FQ bar star. And so like, what do the fixed points of the units of FQ star look like? Well, they're just going to be FQ star, or FQ squared star, or FQ cubed star. So they're like unit groups in finite fields, and all of these finite groups were just products of unit groups in finite fields.
Yeah, so actually like if you then extend scalars, this torus does look like what you typically know as a torus.
Yeah.
Is it's like diagonal. So this will be over like FQ squared. Cool, thank you.
Sorry, what did you say again, Chris? So it's just two parts.
Sorry, yeah, so like if you could ask for what finite groups, say for GLN, look like there might be like, finite groups living inside tori. So if you imagine diagonal matrices and you look at the fixed points of that, you just get F, like the units in FQ times the units in FQ times the units in FQ.
Yeah.
But if you looked at a Frobenius map acting as like Frobenius squared, then you would get units in FQ squared. And so like in general, the twisted forms of the torus in the GLN case look like the products of units in FQ to the N times units in FQ to the M times units in FQ to the K, such that the sum of those equals the N in GLN. And so you sort of see that these things are parameterized by partitions, which is what you sort of hope for if they're parameterized by conjugacy classes of Sn. So it's sort of like the partition in the conjugacy class tells you, like gives you a bunch of chunks, and then the sizes of those chunks give you the degree of the field extension, and then you look at the units, and you take a product of.
So in this case, there's only two choices.
Yep.
FQ star has an FQ star.
Like two partitions.
Whereas,
Yes. Yes. So that T prime is F squared star, and then the other one is F star plus F star. And you see that it's like 1, 1, we've got two pieces, or you've just got one piece that's size 2. That's the partition.
This story should also look like the 2+1 roots unity. And throughout the rest of the talk, I'm just going to denote this torus by T dash anyway. Okay, so this is cool, right? We now have like this notion of like delinguistic induction, where I'm kind of now thinking of this character, oh no, this thing is like a functor from my representations of the torus to the group of
TWF.
So yeah, neat. We have like a way of like cooking up at least like virtual representations of the finite group. So an example. Well, we saw before that when W is equal to 1, that YW was just equal to this, right? Which is just, well, this is a group of finite set of points, this is a group of finite set of points. It's completely like discrete set of points, right? So it only has like cohomology concentrated in degree 0. So we have that.
And so torus, what do you consider varying tori? If they have different tori, which is still that stable, and is it F response?
Right.
Oh.
So then all in our sum over here, all the other like parts vanish of it. We only have like the 0th cohomology here. And so one can identify this space here, or rather this one. So this is the space of all functions. So let's say F going from the finite group G into Q bar. Satisfying so we have G UT, I think. Yes. Oh, no, T here. Okay. So, oh, when we take the theta isotopic component of this, right? With action. So I probably should have used a different, let's call it H. H acts on F. Okay, does this look familiar to anyone? When I have space of functions satisfying this with this action? So this is exactly inducing the character up from the barrel to G. Right? This is cool.
Maybe just a meta comment from the, like this induction where you go from B, take something of T, you pull it back to B, you induce it up to G. You would expect this induction to be useful in this setting because you don't have many double cosets. So like Eke algebra of endomorphisms of this will be small because like the double cosets of B and G, there aren't very many of them, and that's sort of what controls how big the induced representation will be. So like because it's small, it's a good idea to induce from the subgroup. And then if you try and do that for a non-split torus, you can't. There's no natural subgroup containing a non-split torus, which has very few double cosets, except this process works.
So we'll go through this example and then we'll have a break. Yeah. So as I said before, we have the finite group G, and GF acting on this, and then the torus acting on this. And so I want to look now at the particular case where we instead choose this character of the maximal torus, which in this case is going to be this non-split one, and this is the trivial character. For if this is the trivial character, I'm gonna stop writing the coefficients of the cohomology, by the way. Then this the isotypic component of like when this is trivial is simply going to be isomorphic to y quotient this torus. Okay. Maybe this requires proof, but then you'll have to go read, growth and D. But I think morally you can kind of think it of as like, well, if I have some sort of like subgroup in which like I have a morphism that's trivial, then it gives me a morphism on a quotient, right?
Yeah, one way to see why this
Morally believable.
Yeah, another moral, or one way to see it morally is that like if a finite group acts on a space, and say, I don't know, what's your favorite model for cohomology? Maybe it's something that looks kind of like functions, so maybe it's forms, or like something that looks kind of like functions. Then the thing on the left-hand side is like saying functions which are invariant under your group. And the thing on the left-hand side is like saying functions on the quotient. So we hope that if you're in a world where like cohomology classes kind of look like functions, something like this might be true. And so like this is literally true for differential forms.
I suppose you could regard this as like put a T dash up here and regard it as a torus acting trivially. That's all. Get that immediately. Okay. But this thing here equal to this variety. So then, and remember, this is all taking place in the growth of D group as well. But then this was equal to P1 minus the set of FQ points of P1. So then these cohomology groups in the growth and D group is going to be this. Okay. Well, P1 we have a fairly reasonable understanding when it's cohomology. It's it's 0 in odd degrees, right? So only I equals 0 and 2 are going to survive here. And then here, well, this is just a discrete set of points, right? Sorry.
Maybe it's worth noting that like these innocuous looking seeds are very important to make an additivity statement like this work.
And I also think to actually have like sort of bounded complexes as well, right? Because isn't your cohomology only going to live between like 0 and the twice the dimension of the variety?
Yeah,
So
yeah, like it's
probably important.
I think we probably do need the equals finite. Like we've only got finitely many groups in this sequence. And this additivity property fails for ordinary cohomology. It's like you need this compact support.
Yeah. get too much into that. Okay, so we also now know that the zeroth cohomology, as I just said, P1 is equal to, which is just the trivial action. Okay. And well, all the other cohomology of this is going to vanish, right? And P1, that's Q. Let's go. Okay. So then we can go work all this out. So this is W is equal to non-trivial element. And we're looking at the trivial character. So I'm just adding all the H0 terms now. So we're going to get the trivial rep, and then we're minusing off the 1 plus the Steinberg, which is coming from this. And then, well, we don't get any cohomology in degree 1. And then in degree 2, we only have this. So we have this. So putting this all together, we have the trivial rep minus the trivial rep, that goes away. And then this gives 1 minus Steinberg representation. So now we're like kind of going to forget about the characteristic 0 stuff about the linguistic and go up into the modular world. I just do want to say like some final remarks about what we just went through because I can't help myself. There's just so many cool facts about like these characters that I could talk for a few more hours about. But what makes this like especially like cool and also important is that every single irreducible representation of your finite group G will in some sense lie in one of these like virtual representations that you just get from like taking this tori and doing this wacky induction like we've seen, right? So you know you get this like weird alternating sum of representations and like up to a sign you do have an actual like honest representation that lives inside of that. Right. Okay, so now modular delinguistic representation. We've in some sense done a lot of it already because like this Ital cohomology that we've been looking at, well, it already has like values in this p-adic field, right? So we, in some sense, like supplied a bunch of representations now living over like finite field or in some sort of intermediate ring, right? So what I mean by this is like we have a modular cisco K and a little k, right? So like explicitly one should think of what we've just done is big K is QL, potentially with some things added to it. Then O is ZL. And little k is okay. So in this way, we have a bunch of maps of rings. Okay. And then we can also consider cohomology by sort of taking coefficients in any one of these rings, right? That's the beauty of the Ital cohomology, if you will. I'm also going to write it slightly differently again because like I want to get to Perret's theorem and it is a statement about derived categories. So I really should be writing everything in terms of a complex, right? Which we have in cohomology. So we'll write it as this. So this is derived functor. And we can still take cohomology where this is some ring which is say one of these, right? So it's a bounded complex. Once again. And then also finally generate that. And likewise for when you want to consider the cohomology complex of X instead of Y as well, right? And because the torus acts freely on Y, freely on this, we also do have an isomorphism of complexes. Okay. And these are all very nice complexes. Once you stop and consider them, consider them as modules of these things individually, then they're perfect and they're all very good. Which means that these complexes look like complexes of projectors. Okay. And this is in. So then you can define now the linguistic induction in somewhat of an analogous way to what we've just said before. So the induction functors, we now have this sort of derived version of it, well, also denoted by same thing as before. So we take in so I'm going to be working over our intermediate ring here. And it gives us a so we simply just take module, well, I shouldn't say simply really, and then we tensor it up with its cohomology complex. Crucially, we're taking our coefficients in this ring here now. Okay. Any questions?
So this statement about this isomorphism on homology, so to speak, this is like the analogous statement that if I have a group or finite group acting on a space, then the cohomology of the quotient is given by the invariance. It's the cohomology on the invariance in the original cohomology. Okay.
Yeah,
I stated that.
Sorry, it's exactly what we saw before when if I fix this thing, I kind of get one for that action on X, right?
So before you're taking variance, now you're tensoring the band, and you're saying these are the same.
So I was talking about the thing over there.
In the characteristic zero case, well, correct me if I'm wrong, but so we had those cohomology groups, and then we took the theta invariant part of it.
Yeah.
I think you can exactly think of this as over the module, over the ring of the torus, as just tensoring with that character.
Yeah, so it's in both cases we're tensoring, but in this case, we're thinking of the tensor as a very different operating. Here we're thinking of it as we're tensoring with a bimodule to get between categories. Whereas in the other one, we're thinking of the tensor product as a way to take invariance or covariance.
And in this characteristic, TWF does not need to have semi-squares in teacher theory. That's the point.
That's the point.
Yeah, making sure I'm in the right world.
Yeah, I think we might see later if we get to it, but the point is that with these tori, when you kind of want to consider characters of these, modular ones, you'd split it up into a L-Silo subgroup, and then some maximal subgroup in here that has order prime to L. Right.
Is this somehow we're gonna describe this to a subgroup of the whole thing in terms of this?
Yeah, so effectively the rest of the talk is like gonna be on the same thing. But that's not true. So just to like compare with an example that we saw before, is that in this W equals 1 case, we had that these varieties were once again equal to this, right? So then these complexes are just going to look like, so here. Because again, these are just like a finite set of points. It's only going to be concentrated in degree 0. So this cohomology is exactly going to look like flex, right? So, or maybe I need to put a correct break in there.
Well, yeah, but I guess I'm just.
But I'm just simply just trying to translate like what this insane derived statement is, which few of us really understand. I suppose another example, like to check what we had before, is that like this so when I put big K here, the characteristic 0 stuff, this is going to look like the actual cohomology complex that we saw before. So or this is quasi-asymptotic for this, I should say. So everything, we kind of all retain everything that we saw before in the characteristic 0 case. Okay.
This is sort of like remembering the like blue is the complex.
Yeah. So yeah, actually the part that I was going to say next, I just already wrote up here. So we actually do indeed have these. So just denote everything with a dash. So we can split our tori up, our 2 tori in this case. So this one G is equal to SL2, which is probably largely what we'll focus on now. Into like these Sylow subgroups and like these other groups of order like prime to L. So now we want to talk about Sylow subgroups of finite reductive groups. Okay, so I think Chris wrote this down a few weeks ago, and that if we look at the order of the group, we have this formula, right? So this N is like number of positive roots or something, and then this product. And these all just happen to be like cyclotomic polynomials, right? Evaluated at Q. So if we're in the situation where we don't want L to divide the characteristic P, then it doesn't divide this. So then it must divide one of these. Okay. And so in that situation, that's what we usually call like an L Sylow tori, I think that's the correct terminology. Okay. I'm not going to write the definition of it because it's not a very good one. But the L Sylow tori in the group are essentially the ones that like precisely have order that divide like these polynomials. Right? So it doesn't divide just a little bit of it, it divides like the whole thing, I guess.
So should I just think of this as like an L Sylow subgroup inside some potentially non-split torus?
Yes. Exactly. That's kind of the main point, is that if we have these like Sylow subgroups that live in a potentially like non-split tori. Right? And so I guess the main proposition is that so there is a unique integer D where this power here is actually indeed positive, where L does divide one of these cyclotomic polynomials.
There's a unique D.
Yes. What's that? Silo L subgroup of the finite group, now the abstract finite group GS, is contained in some like Silo D tori. Right. Any questions about that?
So there's some like the L large enough, no?
Yes.
So where is that?
So for, as in, so Q not equal to 2 in the case of SL2.
Yeah.
And it's not, yeah, it's not, so like there's some bad small primes. Once you get above that, C-logs are contained in CLO D tori.
I don't want to get too big.
Yeah, exactly. You don't want to get too big because otherwise the whole theory becomes trivial.
I think there is, it's quite technical on how, like what primes to exclude, like in general.
It's like primes divided by R.
Yeah, something like that.
Oh, that would give you a list which includes the bad ones.
But we're gonna see an SL2 example right now, and we're definitely throwing away like L equals 2.
So you say contained, do you mean equal?
Contained inside.
Contained in.
Isn't the COD torus?
No, so okay, this is
Maybe I
probably
missed that.
subtle, right?
Oh, the torus itself is not the COD.
Yeah.
That's a stupid name. The
It's not the
D tori
subgroup of the.
is like a PW. Yeah,
The
exactly.
whole
Yeah.
torus.
So this is like it's an algebraic thing. Right.
Oh, okay. So okay.
This is something that's like living in your actual like algebraic group.
Yeah.
And then what we're saying is that the like of your abstract group of points, there's an L-Silo subgroup there that's I guess you get from like
So it's like saying your L CLO subgroup lives inside a particular torus,
yes inside of your
a unique sort of
group algebraic group.
yeah.
Which I don't know, I guess is kind of cool. Okay, so SL2. Says order as follows. So we said that we're gonna throw away L that divides the defining characteristics, so ignore this. And so if we only have that L can divide this or this, right? So then we'll say let's S. I want to put an L there. SL goes B and B. These are going to be cyclic groups, right? So the goal now is to compute that sort of normalizes and whatnot. That's what I'm going to try to. So if L is odd, so we're going to throw away 2, and if it divides this, then this is going to be L-Silo subgroup of all of SL2.
Alright, it's typically if you break that SL2, yeah.
And if once again our prime L divides this, then this Silo subgroup is going to be a Silo subgroup of all of SL2. And moreover, we have that centralizes these Silos actually equal to the tori. Okay. So
centralized on G or GF?
If you take the centralizer in G, then the answer would be T, viewed as an algebraic group in G. If you view G as GF, the centralizer will be BF, viewed inside GF.
So the main point is that the normalizers of these silo subgroups are gonna look like, I think, some group extended by like a complex reflection group. And I'm just looking at the time. I don't think I'm gonna go through the proof of this now. But we have that if we define this group N and this group M dash. My claim is that these are the normalizers of the Silo subgroups. Well, with the respective ones, right?
Wait, what's that dash?
This is like, so this S here you can think of as your normal SL2 thingy.
Oh, right.
And this is the one that's like commuting your like non-split XL torus. Okay. And these satisfy. So it should square to minus the identity. And it's, what does it normalize? So if I'm gonna write D for like the embedding of the multiplicative group into the torus. So it satisfies that. You can think of it as like, just clips the torus. And this other S is slightly trickier to define, but it too satisfies that it squares to the negative the identity. And because you have like this sort of wacky like rational stuff going on, like as like conjugating with something in the non-split torus. So by D dash, I'm meaning like the take my squared inside of the, not inside, but this, right? I mean this map. And this kind of acts like the Frobenius, which is kind of wacky. I don't really understand it. Okay. And so my claim is that these groups that I wrote down are actually the normalizers of the tori. And moreover, they're actually going to be the normalizers of the Silo subgroups associated with that tori. I think it's not entirely hard to show oneself. You should, yeah, maybe first note that N sits inside of the normalizer, and then if I take something in the normalizer, then I show like the reverse equation, right? So let us recall Bouret's conjecture, because recall that on like one side of Bouret's conjecture, we had like a block of a normalizer, which is exactly why we went through all of this. Write the full name. So this tells us that if D is a abelian, well, D is my defect group, and it is abelian, then we have a derived equivalence between these categories. So dB of O G. Here's a block. And this equivalence here is derived. It's about derived categories. Okay, and so this is what we want to try and look at for SL2, because what I've done is Well, the defect groups are gonna be still of subgroups. And we've just written down all of them in SL2. And we just wrote down what the normalizers are. So then maybe we can try to, investigate this. Or like verify it for SL2. Okay. Any questions so far? Or do you look puzzled?
Yeah, I was just checking one of those and I thought it was wrong and then I realized I made a mistake.
This is also equal to this, I think.
Yeah.
Maybe you'll get that answer. I guess.
Okay, the ring, or which ring was that?
The thing living between the characteristic 0 and the finite material. What do we usually call it? Like a local.
Usually called ZP. So L. That's what I've got in mind.
Yeah, well, it's ZL. But I'm writing the statement generally here. In the case that we're working in. Let me rewrite it. So G is SL2 here. And also let's just even restrict ourselves to the principal block, because I should also write this block back. Because if this is a principal block, then this Brouwer correspondent on the other side is also the principal block of this. Okay. So we should be thinking of this. And then what we'll do is, because this is the normalizer of Silov, show this. And then
Like principal block of that.
I think we'll be showing. This is actually what we want to show now. Because I'm going to restrict to the case where first L divides Q minus 1.
I mean, so on the left hand side, we really mean like GF modules which sit inside that.
Oh no, sorry, I'm so confused. I'm showing that Harshchandra induction.
Like I think the point here is that what you in principle want to know is that in principle you want to know equivalence of principal models. But actually there's an equivalence between more. Namely Harshchandra induction provides an equivalence between ZL
categories.
So
Yeah, go ahead.
yeah, you get an equivalence and then you cut by blocks and you get rows.
So there's like certain blocks appear on the left hand side, like those that appear in parallel induction.
Exactly, yeah.
But where does the S actually come from? On the right.
Well, that's what he's just about to explain.
Oh, fantastic.
Oh wait, you knew that.
Well, no, I mean, I know that that's the problem. I don't actually know how it's solved in this instance.
Yeah. Well, no, because that's exactly the point now, right? Is that, well, we have something here and we kind of want to extend it to something here, right? And that's the name of the game. If you wanted to really go out there and prove Perez conjecture. Yeah, sorry, I should have been more clear about that. Is that what we're going to do is look at Perez conjecture only for, I think, the Harshchandra induction and only on the principal blocks, and only in the case, depending on the time, and only in the case when L divides Q minus 1. Okay, so my first claim is, well, it's not a claim, it is in fact a theorem due to someone else. That so L not equal to 2 and L divides Q minus 1. Then the endomorphism algebra of G, again this is G is equal to SL2. Endomorphism algebra of Harshchandra induction. And I'm sick of writing the S, so let's just So G is equal to Q bar. But this is equal to where N is the thing that I wrote up just up here, which is generated by the torus and this element S satisfying these relations.
Just to nitpick, there's a ZL missing in front of it.
Indeed there is. Yes. So this is kind of gnarly, I guess. So
Yeah, but so this isn't to be expected. Like you would expect to get a like extension of the torus by the Heck algebra. So the dimensions match up, but like
yeah, because on this side here, like this is an endomorphism algebra, but and I suppose a priori, it's also a module, or it's a module of this, right? But like now you're telling me it's like an N module. So what we want to do is somehow like take this thing here, which has an action of T on it, and somehow extend it to an action of N by putting like an action of this S on it, which we can do, and I'm going to be sweeping a whole bunch of stuff under the rug. But okay, so what one can do is pick out a square root of Q inside of these analytic integers, such that square root of Q with me run to 1 or ZL with square root of Q. You can do this by, you probably saw this in a number theory course, by, is it Hensell's lifting lemma or something like that?
Okay, we do it.
we write ZL, but we really mean ZL possibly with more roots view, like with enough.
But we can do this here because L is not equal to 2 and it divides this, so it satisfies 1.
So does everybody, like this is fun little number theory, yeah? Imagine that I give you an equation like, some polynomial equation, and I want to say, does it have a solution in ZL? How do I do this? Or maybe, yeah, maybe another day, but like, just very important, know how to decide whether square root of Q exists in ZL.
So now we're going to define this ridiculous operator, which will look arbitrary because you haven't gone and read several chapters of a book I meant to look at. So let's like write this wacky curly S, and then we will say that it is this wacky curly F minus E, whatever these are, I will define them. So this is an endomorphism of this. So it lives in here.
But what's E?
That's what I'm going to write down. So F is ZL linear endomorphism, and it is defined by of G mod U. Take all the U in the unified subgroup, G, U, hit it with this S, and then U. Okay? This lives in here. And then E is equal to just the sum along all the things I told, right? It's the sum of all the elements in the.
You're saying T acts on this, acting on kind of like from the right action on G mod U?
Yeah.
And you're summing up all the elements? Yeah. Right.
So yeah, G's acting on this, and then this is.
Is it clear that that F is overdefined? Like we picked a different representative. Okay, yes, it is clear.
It is, or maybe it's not clear, but what will help make this seem a bit more motivated is this fancy curly S that we wrote. This satisfies that when you square it, you get negative identity. Right? Looking familiar? And you can move stuff in your tori on it. So by conjugation. Okay. And I suppose it kind of doesn't really exactly add up to this, but I think there should probably be an opposite category somewhere around here.
No, it's exactly what you've written down at the top there, isn't it? Like if you imagine S was inverted.
Oh yeah, yeah. That's all good. So you have like this weird sort of endomorphism living here. And then what we've done is we've just like picked out an element that satisfies exactly, well, that satisfies exactly the property that this S has in this normalizer. So we already have an action of T, and now we have something that looks like this S. So we can make, so we have that as an LT module structure. So we can exactly extend this module structure to an N1 by letting, so S in N. So this here act by this curly S. And so the proof of this proof here is finished by something that's not at all obvious or trivial at first, but I'll write it anyway, is that one should note that this endomorphism algebra. Here, write this correctly. Then decomposes as follows. Times this action of yes.
The LP plus the first one though?
Yes, the first one just the envelope.
Sorry. So we have this part here, and then we have this like curly S action here. And the claim is that this is
Surely you mean endomorphism is a G module, no? It's in on G.
oh yeah. Yeah, I think you're right.
Oh, yeah. On the left hand side.
Yeah. And so that is the proof of this fact.
So in this instance, you're looking for some exotic S action, and you just check that way. And then you say, I have not achieved enlightenment. Where does this come from?
Where this comes from generally.
Yeah, like is this known the general productive groups? Like how much of this setup is known to work?
Well, the paper that Jordy went through last week, so belonging in the work here, the categorification of SL2. So they proved the rare Abelian defect conjecture for the symmetric group and for GL and FQ.
Oh, okay.
Using like I think something of this effect. I think generally the the idea is that like between in Bray's conjecture, we have these like two bounded derived categories, and we want to say that they're equivalent, right? So there is a functor going between them already, but the claim is that there is a Deligne-Lustig variety whose complex gives you that equivalence. And I think the current sort of strategy about going about this is like, you have like these normalizers of Siller subgroups look like, you know, stuff plus a complex reflection group. Then you get like some weird braid action. It's all crazy.